am teaching this lecture for the purpose, if any, out of the box questions comes from this topic. But so far, no questions have come in any competitive exam from this topic. Actually, the matter in MOS capacitor is sometimes replaced with degenerately doped semiconductor. As we know, degenerately doped semiconductor somewhat acts like metal. However, degenerately doped semiconductor will introduce some changes in our analysis. It will be best to teach you through a question. Rather than watching this lecture as if a movie is going on, you should pause the video and try to solve this problem. I hope you have at least tried to solve this question. In the question, it is nowhere written that it is a MOS capacitor, and the same way happen in exams also. Sometimes there will be no direct indication about what type of device is it. You have to analyze the situation and determine yourself. Here, you are supposed to judge by looking into the energy band diagram. As in the middle, there is silicon oxide, which is an insulator. That's why we can conclude this arrangement is of MOS capacitor, and the formulas for MOS capacitor will be valid here. You should also know not all oxides are insulators. Few examples of oxides which are insulator are silicon oxide and aluminum oxide. The second thing is whether this MOS capacitor is ideal or not. Interestingly, there is no significance of this diagram except for the fact that we can determine whether it is ideal or not. In the question, it is nowhere written that there are charges within the oxide. Since it is not written, we will assume that it is ideal with respect to charges at least. And the second condition of non-ideality is metal to semiconductor work function, which is actually dependent upon the position of Fermi energy level. But as you can see in the diagram also, the Fermi energy level of the two semiconductors lie exactly at the same energy band. As a matter of fact, the dashed red line within the oxide is present just to represent it clearly that both the Fermi energy levels are at same energy level. So, both the conditions for ideality are valid. Therefore, it is an ideal MOS capacitor. The threshold voltage will be equal to voltage drop across the semiconductor Y plus voltage drop across the oxide plus voltage drop across the semiconductor X. Potential drop across the semiconductor Y is nothing but the surface potential plus the voltage drop across the oxide, plus it is also provided in the question that the potential drop within the semiconductor X is 0.2 times the potential drop within the semiconductor Y. If it was a metal, then the potential drop will be simply put equal to 0. But here, in this case, we can write potential drop across the semiconductor X will be equal to 0.2 times the surface potential. So, threshold voltage will be equal to 1.2 times surface potential plus potential drop across the oxide. It does not matter whether we have ideal, non-ideal MOS capacitor, P-type or N-type substrate MOS capacitor, or whether there is a metal or degenerately doped semiconductor on the other side of oxide. But at threshold voltage, surface potential is always equal to 2 times of Fermi potential. We also know for N-type substrate MOS capacitor, the Fermi potential is equal to negative of thermal voltage into natural logarithm of doping concentration divided by intrinsic concentration. After calculation, you will find the Fermi potential to be equal to minus 369 millivolt. The formula for threshold voltage can be derived exactly in the same manner as we have derived in normal cases. Putting the value of different parameters, we will find the threshold voltage to be equal to approximately minus 1500.29 millivolt or minus 1.5 volt. It should be clear to you that we always consider charge on the metallic side of the MOS capacitor. The reason is very simple. Consider this very simple configuration in which from KVL we can simply say the gate voltage is equal to voltage drop across the metal, voltage drop across the oxide plus voltage drop across the semiconductor. But again, observe it very carefully. This equation from KVL is valid for different voltage drops as per the shown polarity. If we consider the voltage drop across the oxide, we can see the positive side lies on the metallic side. Therefore, to find the value of the voltage drop within the oxide that should be put in this equation of KVL, we have to find voltage drop in terms of charge on the metallic side. However, generally, the charge on the semiconductor side is provided, and the same formula we have just used in our question. This question was quite easy. Very few books consider this topic, and that also only theoretically. Like, they will talk about what are the advantages and disadvantages of having degenerately doped semiconductor in place of metal. If you are clear about the derivations of different formulas, then you should not panic in the exam if any question comes which is quite different from the questions you have practiced. One thing we can conclude here, since there is a voltage drop within the degenerately doped semiconductor, which was not the case when there is a metal, which results in the increase of threshold voltage. In the short notes attached in the video description, I have not written any question. If you find this question interesting and quite important, then you should write it in your short note.